welcome. Oh, the date's wrong because I gave this same chat on Monday at the Learning Center down in Burlington. And you are going to have access to this, so you have all of my information and all of All Learners information as well. Here are All Learners common agreements. Please have an open dialogue, be fully present and engaged, and please appreciate that learning is a process, not an event. There are Zoom protocols, but I did not put those in here, but that's okay. As I said, we're going to go ahead and work with Algebra Tiles today. I thought we had a very nice introduction this morning, a few minutes ago. And we're actually going to connect to that, I think. And there we go, that's me. And here's the plan. So we're going to play with some tiles, and you may have tiles in front of you, but if you don't, I have some ways to use virtual tiles that I'll share in just a moment. We're going to model integers, expressions, distributive property, one-step, two-step equations, multi-step equations, and depending on, it doesn't sound like we really need to go into bi and trinomials, but if people want to and we have time, we can do that too. I then have some routines that we can use and a couple of extra resources to share at the end. Okay, so I think the first thing I want to do is offer you a moment to think about how you want to work with the materials today. So I noticed Kim shared that she had her Algebra Tiles out with her. So if you have Algebra Tiles, you can just kind of put them out in front of you and you can do it that way. If you don't have Algebra Tiles, on page 7 of the slideshow, you can go ahead and access Mathsbot or Polypad, and those are both virtual applications, or you can make a copy of my slideshow, and I have, it's an interactive slide, so you can actually use each slide to solve the equations right on the slide. But you'll have to make your own copy because I'm going to be doing that on the slideshow in front of everybody. With that, you're probably, if you're going to do it virtually, you're probably going to need to split your screen or switch tab to tab, which I think we're probably all pretty used to and pretty good at it. So I'm just going to give you maybe 2 minutes to go ahead and do one of those. And I guess just say all set, or you can put it in the chat and just let us know when you're ready to keep going. So when you're in the slide deck, if you go ahead and create a shape, you know, if you're going to just do integers, maybe you'd go ahead and you would have, I have to color it, you know, color it whatever color. The green one is going to be a positive one. So what I do is I go ahead and copy it and then just paste a ton of them. So I don't know, as long as I have a bunch, I just go ahead and grab them. And when you right click, you can align it horizontally. And then I right click again and I can align it vertically. And so now I have all of those squished into one little pile. And then if I'm not sure if I'm going to have enough, I can just go ahead, I can highlight it again. And I can copy and paste the whole pile and then put it back on top. And so now I have twice that pile in a little pile, and every time I pull from it, I'm only pulling one tile at a time. So right there, I probably have 25 tiles. So as long as I'm not asking a student to build something with more than 25, they're never going to run out of tiles. So you could actually put, like, pretty easily put 100 tiles there. They'll never run out on this slide. And then once you build the template, then just copy that template slide, and all of your tiles that you need for your building are already there and it's already created. So it's kind of your own little virtual slide or tile deck. So yeah. Okay, so first thing we're going to do, if you're new to Algebra Tiles, it's not really a guessing game. It's kind of, okay, well, we have Algebra Tiles. We have some red tiles and some non-red tiles. Depending on the manufacturer, they don't always match up in colors. All of them will have a red side, and the red sides are negative, and all of them will have a non-red side, and they're the positive values. So the little squares are one unit. The long skinny tiles, the rectangles, are 1x, and the large ones are x squares. And yeah, all right, so I already kind of played on this one, but what I want to talk about is I want to talk about something called a zero pair, and take a moment and try and build something that you think might be called a zero pair. And maybe someone would be kind enough to unmute and explain what they have.
I just put one red unit and one minor white unit together.
So a red unit, and for me would be a yellow unit. If we have a negative unit and a positive unit, they're exactly the same size. They're going to zero each other out. So think about if I have an x square and I match that with a negative x square, they're going to zero each other out. There's two of them, so we call it a zero pair. Kids can actually explore and discover this, and it's pretty fun for them to do that. And it's a really handy, tool that we will need in a little while. All right, so the zero pair is an important thing, and it is fun to explore with the kids, and we, again, will definitely use it in the future. So we're going to start out with integers. And what we talk about is, this is one of the models that Steve mentioned earlier. I think he mentioned. I was actually doing a little work and listening at the same time. So, but one of the models that we can use to support integer learning is using these tiles. For this example, I don't need any of these. I'm just going to get rid of them so they don't get in the way. So I just need the little squares. So I have 2. So I'm going to start with, so I go ahead and I build 2. And then I'm going to go ahead and add to my my mat. Sometimes I'll give kids just a mat to work on, and we'll go ahead and we'll add 3 negatives next to it. And then I'll be honest, it's been a long day for everybody at this point, so I can talk the whole time, but I think it's probably more fun if you guys maybe, if it's quiet in your background, you can unmute and just talk. If it's not super quiet in your background, you could go ahead and unmute when you have something to say. But what do you guys notice once you build that?
That you have two zero pairs that are in there, and then you have the one red or negative left.
Right, so we have 2 zero pairs, and at this point, when the kids have played with the idea of a zero pair, they're going, well, a zero pair is 0. What's the value? And the only thing that doesn't cancel out is that -1. So if I have 2 plus -3, my answer is -1. Thank you.
This model kind of reminds me of when you're talking to first graders and second graders about how much more is 2 than 3, right? But it's kind of the same thing, but now it's applying it to integers in a weird way, right? Like it just, that model made me think of that immediately.
Right. With this, if you're on a smart board, I go ahead and write, just like circle the two zero pairs. I might put an X next to them. I might write =0 next to them. I don't have a smartboard app right now, so I'd probably just mess the whole thing up if I tried to write on it. All right, so the next one we have is I think. Yeah. So -2 and -3. Go ahead and build that and see what you notice. And I'm going to channel my messy daughter, because we know a lot of our students are not going to line up their tiles in a nice array. And when you do that, do you notice any 0 pairs?
So Kathleen, what I was thinking about was I was supporting students with a problem similar to this within the last couple of weeks. And they had an aha moment of like, I don't know what to do now because there aren't any to mark off. Like that was a sticking point where they just got stuck because all they had was negative.
And Rachel, how did you get them by that stuck point? Or did you get the, I assume.
I don't know if they extrapolated further because of the situation that we were in. It was somewhat of a one-off. But in the moment I was like, well, if you don't have anything to zero out, then what do you have? And they were able to give the answer then, but they had that moment of like, uh-oh, the next step isn't available to me.
Right, and so sometimes it's just go ahead and build it, and what do you notice? Right, and I notice I have 5 red chips. Well, what's the value of a red chip? Oh, that's a -1. So then what do we have there? And often they'll come up with, oh, right, it's just -5. I didn't have any 0 pairs. Yeah, but that's an interesting, you don't usually think, oh, they're going to get stuck because there aren't 0 pairs. So that's really interesting. Thanks for sharing.
Model helps kids really understand the difference between adding 2 numbers of the same sign and adding 2 numbers with different signs, because it feels so different when they're doing it with just straight numbers, and it's hard to see why it feels so different. But in this case, it's really obvious that when you have all of the same kind of tile, you're just combining those tiles. You don't have to zero out or cancel anything.
Right, right. So you're kind of leading me to the next slide, which says, which says 2 minus. The other ones that we've been adding. So when we add, we just put things onto our mat or onto our board. And this one we have, well, I have 2, so I can go ahead and I can build that too, right? And this is where, oh, my pen's not working. There we go. So I build my 2. I have 1, 2. But then it says I need to take away or subtract -3. But I don't have -3 to take away. Where am I going to get them?
By adding some 0 pairs?
Try it, see if it works. How many 0 pairs would we need to add?
And how would you explain to students why you have to add them as 0 pairs?
I never have.
Okay.
I leave it open.
Mhm.
And I say, wow, I only can put 2 on there because it says I have 2. Now I have to take away 3 negatives. What are we going to do? And the kids explain it to each other. I've never done this where they haven't come up with, put some 0 pairs on there.
You're building on what they know about adding 0 doesn't change an equation. That concept got built in early elementary, and you're kind of building on that.
Right, right. So someone will come up with, Or you can back up. You can back up in your learning with the kids. If you're sitting there and the private reasoning time is going on and on and on, you're like, all right, I can't wait anymore. There's too much wait time. You can go back with another example and kind of say, well, what happens if I have one and I add a negative? What's the value of this? And you can kind of lead them to it. But I really don't think I've ever had a class where I've had to tell them like, hey, don't you remember about the zero pair? They've always come up with it. And even if let's just say they only put 2 of them on there, we can go ahead and say, and sometimes you can build a little trash bin on the side. Some of the old apps that have gone away with Java had a little trash can. And so when you didn't need a tile, you would put it in the trash, it would disappear. But I just put it over to the side. So now I have 2, I need to subtract 3 negatives. Well, I'm gonna subtract, I'm gonna take away 1 negative. I'm gonna take away another negative. Oh, wait, I don't have enough to take away. I've only taken away 2. And the kids will go, add another 0. Well, ideally they will, and have fun with it. And so we add another 0 pair. And again, as Erin was saying, we're not adding anything to the value, we're just putting 0 next to it. I take away another negative and we have 5 positive tiles. Comments so far? I'm gonna go ahead and let you guys go ahead and do, then I'm assuming the next one is, what do we have? Oh, that was it. Oh, we can't go there yet. So adding and subtracting. Does anyone have any comments or questions? Or if this isn't, it's not going to work for every single kid. And some kids just want to go ahead and tell you the rule that their parents told them and go by that. But and some strategies are to have tiles out, to always have a red and a non-red color pencil out for kids to use, so that they can model it on their own. They tend to want to stop having tiles in front of them after a little while, and the colored pencils are really helpful, I find. So it's a good strategy before they get to the, oh, I know a rule, I figured out a rule, I know something that always works. And again, just like we heard earlier, is, I'm always asking kids, why does that work? Because we know that if they memorize the rule, it's only memorized for the moment that they need it. And it doesn't typically stick unless they understand where it came from. So are we good with adding and subtracting for now?
Kathleen?
Yes.
It's Amy Ring. I just wanted to say, I think it's important when using the model, I found, to really emphasize the starting value. So you start with nothing. And if I have +2, because I know when I've used this before, kids will say to me, well, just put 3 reds there and take them away, because it's takeaway, So I say, okay, well, if I put 3 reds there, now what am I starting with right now? What do I have? I don't have 2 anymore. So that encourages them to create those 0 pairs first and then take away, leading to the +5 that's left.
Mm-hmm.
So, and that kind of mirrors, because same thing on the number line. Like if you give them +5, they want to go to 5. And I go, well, where are you starting? We're starting at 0 and we're going +5. So I think sometimes with the models, that's what gets in the way. We're starting with nothing. What's the value of nothing? Okay. What's the value of 2 with this model? And then that can help them see that I can only take away those 3 if I have 0 pairs to take away from, I guess.
Mm-hmm, mm-hmm. Yes, I can see what you're saying. Yeah, depending on your classroom, depending on the needs of your classroom, you can certainly also start with just building integers.
Mm-hmm.
Let's build. Okay, now I'd like to have 5 out on the table, have them build 5. Okay, now put those away. What do you have now? I have nothing. Okay, let's put, let's build -7, and they pull 7 red ones out. What do you have in front of you? -7. Okay, clear it out. What do you have? I have nothing. or zero. So yes, thank you so much, Amy, for sharing that.
Kathleen, I have a question. When you're modeling this with tiles with your students, are you also at the same time modeling it on a number line, or is that like a different part of this lesson progression for you?
For me, I use these first.
Okay.
I have discovered, I also have a little like workshop on integers, which takes a whole hour all by itself, or more. So there's also a really powerful game called Floats and Anchors. And its model is a little bit of this integer model, the chip model, but it's superimposed on an elevation model that starts at sea level is 0 and below sea level is negative and above sea level is positive. So it actually superimposes it on a vertical number line, which if you do it in the beginning of 7th grade, the kids aren't too old to really get into the game. But if you do it, I found last year we used that as an intervention in really small groups and it worked really well. And this year we tried to do it in some intervention groups in 8th grade, and the groups were kind of on the bigger side and they were all way too cool to play a game about a pirate ship sinking and floating. So you kind of have to read your audience. But so when I've taught it only with tiles, I only did tiles with the floats and anchors. I saw the power of using both models. And so, you know, I think read your room. I think it's a great way to do both. I think I also have you know, we have to be careful about overloading our kids with models at the same time. So if you're kind of just introducing the chips, maybe spend some time with the chips and then bring the number line in and then say, well, how are they the same? How are they different? Who likes which way? Have them share why, those types of things. But once they have the number line, then you could have one student modeling with the chip model, another student modeling with the number line, and you have more opportunity for the kids to understand it in their chosen model.
That makes a lot of sense. And starting with the chips makes sense too, because it's the most concrete of all the ones of all the models that you could use.
And it's one they've been using since kindergarten.
Yep, exactly.
Right.
Thank
And that's
you.
one of the other reasons I really like it, because it's so connected to models that they've been using and adding and subtracting. They use chips to model multiplication and division with their arrays and groups and loops. And so I'm a fan of the Algebra Tiles because you also can bring it through high school. It's one of those, it just has such a wide range of use. So you don't have to reintroduce the manipulative. They already know it. They already know tiles. We're just adding the little piece that along our tiles, an unknown, and you know, in the red's negative. So that's kind of new for the kids. Okay, moving on to, what do I have? I have multiplication, right? So this goes back to what kids learned in 3rd and 4th grade when they're building arrays. So the way I offer this to kids is I have 3 sets of -3. So when, you know, and again, you can just ask kids to build it. What do you think this means? Because they often know, and you can use a little star or a dot in 7th grade. Most kids know what that means. You could just ask them to build it, see what they come up with, and have them explain, why do you think that works? Does it work? Who agrees? Who doesn't agree? And what we'll end up with usually is an array, a 3x3 array of our negative chips. And I'm going to be hopefully faster about this. So again, connecting it back, say, remember when you built arrays back in 3rd and 4th grade when you were learning about multiplying? So what did you do? Model it with whole numbers first. How do we build a 3x4 array? How do we build a 5x8 array? You know, maybe not that big because then they have 40 chips, and we definitely don't have 40 chips in front of us, and it takes forever on this. So you'll notice on this electronic copy, all of my numbers are really small because the dragging gets a little monotonous. You can go a little bit larger when you have the tiles in front of you. But I do think if you keep the numbers on the smaller side, it's a little bit easier to build them, and it's a little more efficient for the kids to build the smaller numbers. Where the multiplication, I think, gets tricky is when the first number is a negative. And that's what I have in the next one. And so the way I go about it with kids is I say, okay, let's ignore that first negative. Let's not say we have -4. Let's say we have the opposite of 4, because that's another way to talk about negative. And that's where the number line comes in. If you have 4, what's the opposite? -4. So in this case, I talked to the kids about, okay, well, and if I were in person right now, I'd put my thumb over the negative in front of the 4. And so let me see if I can do that. I'll hide it. Fill it up with that. And I'll just go, okay, well, let's hide that for a minute. Now what do we have? And at this point, kids will go, oh, well, you have 4 sets or 4 rows of -3. And we can go and build that. Right. And then we can copy, whoops, copied too much. It's too long. Let's get rid of that. So I have 4 rows of them, right? And kids will go, okay, yep, you have 4 rows of them. We're good with that, all right. And then I say, okay, well now, what's that negative in front of the 4 mean? And if you've done some modeling on the number line, if you've talked about opposites, and ideally in 6th grade, they know the opposite of 4 is -4. But well, I have the opposite of that. And how would I show that? How do we show the opposite of what I have there?
Can you just flip them?
Yeah, exactly. And if they're not getting that, you can take a step back and say, okay, well, if I have a -1, what's the opposite of a -1? And you know, they will absolutely go, come on, it's +1. And you know, you have 2 chips and go, okay, well, what if I only have this chip? What do I do with this chip? And they're like, oh, just turn it over. Like, oh, could we do that to those 12 negative chips right there? Can I turn them all over? And they're like, yeah, you can turn them all over. Is that the opposite of? They're like, oh, yeah, that's the opposite. And, you know, and usually kids will come up with that. But you can lead them to it by doing the 1 chip and what's the opposite and flipping them. On the apps, I believe you can just click them and they change the color, at least the good app that I used to have. But if you're on this, what I would do is I would just highlight all of them and change the color to the opposite, instead of trying to flip through, you know, instead of trying to build the whole thing all over again. I just change the color, bam. And then we go, oh, okay. So that, you know, that's the other thing. I think ahead of this, you have to talk about what is the opposite versus just what's negative, and being able to interchange those 2 ideas. And the number line and 6th grade learning about integers can build that. If it's you teaching 6th and 7th grade, it's great because you can say, hey, remember last year when we, but if it's not you, you're not quite sure, and say, well, how did you talk about it last year when you learned about negatives, and show it on the number line, and flip the chips over. That's the opposite side. Here's the opposite side. And what I find that is really helpful for when we move into distributive properties, or distributive, so which we're going to go next. How is this so far? Okay. Got a couple thumbs. All right, thanks. Let's see, what do I go to next? Oh, expressions. I'm going to skip ahead to distributive, but oh, there it is. It's way down on slide 21. If you're on my slideshow, I'm just jumping down to 21. Slide 21. If you're if you're using an app or in front of you, it doesn't matter because all right. So again, I go back to the array that the kids learned. What does 3 times x plus 2 really mean? It's what do we have? And when you ask the kids, what does it really mean? So what do you think kids would say if you say, what does that mean?
Probably 3 groups of x plus 2.
Okay, and then, so can you build 3 groups of x plus 2? And usually kids can do that. As I just did this and I'm rethinking, kids would need to have experience with combining, doing some sort of expression work, which I believe is in 6th grade. Doing a little bit of expressions, a little bit of equations. And so you'd have to have some work around that before you jumped into distributive, but I wanted to piggyback on the negative with that we were just doing. So I wouldn't jump right to here with students at this point. Because at this point you have, okay, well, what do I have now? And they count things up and they have 3 x's and 6. And then kids will start to recognize the quote rule, the distributive, the sharing out property, and they'll want to stop building. And it's when I'm a big proponent when they don't need to build things anymore, I don't make them. You know, I do ask them to show a model to prove that or prove it to me. But then once they can prove it, models can be time consuming. So I really, once they're ready, it's fine with me. So this is the one I wanted to kind of piggyback onto, the next one, which is the opposite of 3 groups of x plus 2. And, if you've had experience teaching this with kids, this by itself, kids are like, no problem, I got this. It's the opposite of what I just had on my last one. Just flip them all over, I'm all good. But where it really gets tricky is when there's another number in front of this expression, of this term. So if we had 4 minus 3 times x plus 2, that's where the kids really struggle. And that's why when I'm building experiences around this with kids, I always, I'm just gonna look ahead and see if I have it. I don't even think I have it here, but when I do that, I always build it 4 plus the opposite of 3 groups of x plus 2. I'll always do it that way to build that in. So they're like, oh, and then you go ahead and model it like this. Because then they've had all of that experience of, well, and then you can say, well, what is it? What's it similar to? And then they can make that connection to, oh, that's the same thing as when I have 4 plus the opposite of 3 times x plus 2. But if you go right here, they're going to want to take away 3 from the 4 before they take 3 groups of -2 and flip them all over. So you have to be careful about the way you build that, and build their capacity to understanding that this right here, when we talk about it, is the opposite of 3 groups of x plus 2. Does that make sense? Yeah, and it's tricky because I will say not all materials will right? So you're like, okay, well, I got to practice this. I have a binder, I have this worksheet, pull it out. They're not all going to be super thoughtful. So look at them first. Make sure, how far along are you in this? With the learning with the kids? Do you still have struggling learners? With your struggling learners, keep them leave that plus in there for them. And then they'll get to the point, and with all of that experience, that I just remember when I first started teaching, I'll totally admit it, every subtraction change to adding the opposite, just memorize it and do it. You know, that's what we did. You know, I'll admit that was 25 years ago and I've learned a lot since then. You know, but we need to build that capacity so the kids can build that understanding of, oh, when I have, that's just like when I don't have something in front of there. If I don't have like a 3x plus the opposite of 3 times x plus 2. Okay. So I'm gonna scooch back to, I'm looking at the time, it's 5, we have plenty of time. So I kind of feel like we're beyond building expressions. Do people want to go through building expressions, or are you fine? It looks like people who have their cameras on are saying it looks okay. We can move through this. Can always go back. Oh, you know what? I do want to, hold on one sec. I'm looking. Okay, I do want to build this one, or I want you to build this one. I will admit, when I built this, I had like a thought process, but I got away from it. And so I want to come back to it for a minute and reset myself. I want you to build this, and I want you to think as you're going through how you're going to build it. And I'm on page 19 of my slideshow if you're using the slideshow. I'm curious if someone would feel comfortable to go ahead and share that once they got to what I have on there, because I'm pretty sure everyone did. What did you do next?
Kathleen, I thought that the rectangles represented X's.
You're right.
Okay.
I'm sorry. Totally me. No wonder y'all are silent. Thank you, Rachel.
So what I did is I started combining like terms.
So from here, you start combining like terms?
I started looking around, yeah, to see like if I had like terms.
And what did that look like for you?
For me at that point, so I got what you have there, and then when I saw the -5, I checked to see if that was going to end up with any 0 pairs that were, if there were going to be any positives with just the non-variable pieces. The
I'm curious if anybody else got to that point. And
I used what you just said. So I was thinking I wanted to make this plus -5 instead of -5 so that I could pull out 5 of the red ones, because I don't have 5 positives to put in my trash bin.
right. Okay, so that previous learning with when we have the opposite of 5, what are we really adding there? That came into play. Did anyone put 5 0 pairs on?
Oh, I didn't even think of that.
Because in the progression of as we're doing this, right, we have 2x squared plus 3x minus 5. Well, I don't have 5 there to take away. So when I'm in a classroom with students, I'll go ahead and say, well, where'd you take them from? Are there any there? Where'd they go? And so I'll be like, well, then what are we gonna do? And you need to go ahead and have them here. Yeah, so I'll go ahead and add my 0 pairs. Oh, whoops, that didn't work, huh? How do I get rid of that? I don't know. Sorry about that. Right, so then from there, now I can take away 5 because I have them there. Before that, I didn't have 5 to take away. So I can put it over in my trash bin. There. Now I'm at my x squared. I can add another x squared, right? Now I need to take away an x. Do I have an x to take away? I do. There's one right here, so I'm going to go ahead and take that away. And now I'm going to go ahead and subtract another 2. They're not there. I don't have 2 more to take away. So I need to go ahead and add myself another 0 pair. Have another 0 pair. I now can go ahead and subtract 2. 1, 2. And now that we have, I've built my expression. Now that I've built my expression, I can try and simplify it. So even though I think sometimes we look at this as teachers and people who have worked with the integers a lot, and we just go, oh, well, yeah, I have -5 and -2. But I think we have to be careful about building that knowledge with our students because they're often not at all comfortable with doing that yet. So encourage that 0 pair. Where how can you take the 5 away? You don't have it. And what Erin said earlier was nice because depending on your experience with your classroom up until then, students may go ahead and say, oh, well, from our other stuff that we worked at, that's just like adding 5 negatives. And if the kids come up with that and they can prove it, and then you can go ahead and just as Steve was saying earlier, did anyone do it a different way? And someone may have done it the way Erin did it. And someone may have gone ahead and done their 0 pairs. And what's great is to have all the multiple entry points and they can all come out and say, oh yeah, I'm where I need to be. I know I'm getting it. I'm getting there. And so it's really nice to have all those different examples. Did anyone do it differently than the way the adding 5? Did anyone think of it differently?
I didn't think of it differently because one of the ways is my thinking, but in watching you do the 0 pairs, I just was kind of struck by how, as an adult thinker to this, I can flip back and forth between the subtraction sign being a -5 or saying subtract 5, and how much I would want to encourage that flexibility in students, and how your way of showing it's the same as adding -5 or putting those 5 0 pairs, how it really helps you see that you can actually make that flip back and forth. I just really appreciate it. I didn't even think about it, showing it that way.
Yeah. And yeah, I mean, yeah, we're beyond the learning of this. And that's why sometimes it's so tricky. And depending on your age, you may have learned it as a rule. Like you may not have built your own understanding of this. It's just, this is how it is. The math gods say it. All right, let's see where I am. Where are we now? I'm going to go ahead. I'm just going to make sure as far as the modeling goes. Oh, this one's a good one. Distributive. I have, and this is what this is the one I actually just played with. This, remembering to start our modeling with that adding the opposite of 3. I think that's really important. I'm just gonna, okay, oh my goodness. I was like, boy, I thought we had a lot more. Okay, so the other really powerful thing that Algebra Tiles do is if they allow us to model. How many people, a show of hands or just a yay or nay, how many people are using open up resources in 6, 7, 8? Okay, so they do not use Algebra Tiles. They use something called hanger diagrams. I'll be totally forthcoming. I'm not a big fan of the hanger diagrams. And the reason I'm not is because I feel like that manipulative, it's an online one, I think. I don't know if I guess they draw them too. It's not super transferable. Kids are used to using tiles a lot. We can use them for a lot of different things. And so I feel like they're comfortable with them already. In modeling one-step equations, a lot of times I'll give a kid a mat and then it's easier in person to do this, but I'm going to stand up anyway and try and get myself in the screen. I'm sure if you guys have, if you've done any equations, you're always like this. Like if you have this on this side and this on this side, they have to be balanced. I'm always doing that in the classroom. And I'm like, okay, if I take 3 away from this, I'm out of balance. What do I have to do? So one of the visuals that I do is I give them a mat with a scale in the background, kind of shaded out. So it's kind of like a draft in the background. So they can still, it doesn't distract from what they're doing. Another simple way, because you don't want to have kids always drawing skills, is to just put a line down the center like I did on the slide right here and build, say, okay, well, I'm going to take this equation, put it right over there, make it line up better. And right, the equal sign is the line. So if we go ahead and build this, I will say at this point, most kids will have gotten to the place where the x minus 3 is just x and 3 negatives, because they've already had a lot of experience with the integers. They've already had a lot of experience. They should have experience with distributive by the time we get here. And so most kids will say, okay, well, I have an x and minus 3. Now, if they don't, build it with the negative, with the 0 pairs. It's absolutely totally fine. And then the equal sign, because that's the balance, you're in balance. Your head's the equal sign. And then we have our 4 on this side. And let's see. There we go. And then, we talk about the goal. We're trying to find out what x is. X has a value for this situation. There's an answer for x. It has a value. What's the value? And, if as we're building this, we do simpler ones, I kind of set you guys up a little bit harder. Whereas a yellow and a yellow, you can take them from both sides and they're still, right, in balance. But I don't have anything that's the same. So what can I do? Any ideas?
You take the reds and move them to the other side. You make them the opposite on the other side.
Why would that work? How can that work?
It's because you have a -3 or take away 3 or a -3. Sorry, my dogs are gonna go crazy. And you you've got to get them on the other side of the equal sign. And in order to do that, they become the opposite. And then you have
So-
X, so you have X equals the total.
So when I put them over here, it miraculously turns yellow. Can someone help me to understand how it can jump the other side and turn yellow? Go ahead, Kim.
I think that if we're wanting to take -3 off of the left side of the equation. Wait, no. No, so if we want to take -3 off the left side of the equation, to keep it balanced, we also have to take -3 off the right side of the equation. But we don't have -3, so could we make 3 0 pairs
Let's
on
give
the
it a
right
try.
side of the equation?
Let's try. There's 1 0 pair. I'm just gonna copy and paste them. I put 3 0 pairs on this side. And again, I'll go ahead up in front of the kids. I'll be like, I just put 3 0 pairs on this side. Am I now out of balance? I'm like, no, it's 0. It's like, okay, I'm still good. That's a legal move. It's okay. The police aren't going to come after us. We do talk about the algebra police in my room sometimes. They're not coming after us. So how does this help us?
Well, I'll continue with this one, although I just had a completely different thought. Now we can take 3 reds off of both sides.
Oh, so I have on both sides of my, I'm out of my camera, there we go. On both sides of my equation of my scale, I have 3 reds. So if I take a red off of that side, I'm now out of balance. So I need to take a red out of this side. Is that what we're saying, Kim?
Yeah,
And you're being fast about it. So you're saying just take 3, right?
right. But then as soon as I said put 3 0 pairs on the right, I thought of a different way, and I'm wondering why you might choose one way over the other. And the different way was, if I want to only have the X on the left side, I could put 3 positives on both sides.
Okay, Kim, hold that thought for 1 second.
Yeah.
So here, Kim gave us an idea. She said we want to take 3 away from both sides. The right-hand side didn't have 3 negatives. So we added that 3 0 pairs. Did anyone see an issue? Was there anything illegal going on with what Kim modeled there for us? Does it seem okay? All right. So in this case, the way Kim modeled it, we end up with X is the same as 7. Do we agree with that? Okay, so I'm going to come back. Now Kim goes, wait, I think I found a more, would you say it's more efficient, Kim, or are you just not sure?
Yeah, I think it's more efficient.
All right, let me back this up a couple before I did the 0 pairs. Okay, Kim, go ahead.
Well, so then I was thinking, I want the X by itself on the left side. So in order to 0 out the 3 reds, I can put 3 whites on the left side. But
Oh,
if I
so
want to keep it to in balance, I also have to put 3 whites on the right.
Kim asks me to add 3
Or 3 positives.
3 positives to both sides of the equal sign. And she wants to do it on the left hand, but if she does it on the left hand, she says, oh, well, I have to do it on the right hand to keep the balance, right? When we do that, what happens on this left-hand side? Is it magic?
I don't know, kind of.
Yeah, kind of, isn't it? This is one app that when you like pull the one over to another and then they like bing, they go away. It's a great, it is almost like magic. But since we don't have that, we've now gone ahead and created 3 0 pairs. So 0 0. So can I just go ahead and move those away into the trash can so they're not part of the equation anymore? Am I still in balance? I'm still in balance, and I still come out with the same value for X, X is the same as 7 positives. Yeah, nice. Let's bump down to, oh, I want to come back to the moving a red to the other side is the same as moving it over and flipping it. That was totally accurate. It's completely true. But I will always ask a student to prove it to me. Why does that work? Why are you doing that? I don't understand how. And having them go back to say why it works is really powerful. Because we know it works. We know that that works. But having them prove it to you and explaining, having them to be able to explain it is really nice. All right, so next one, 3x's equals 6. Again, I love having the equals, the balance, the equal sign. I'm gonna move this over here, draw my little line to say, okay, I have a left and a right side of my equation. I go ahead, I drag out my tiles. I have 3x's over here on the left-hand side. And I'm gonna do something very intentionally. So what do we get?
What would you match up even yellows to the X's?
Okay, so when you say match up, how do you want me to do that?
So if you put them across from, you know, if you put 2 yellows across from each green.
Are you having me be organized?
Well, yeah. So I guess when it looks like that, then it's showing you that one of the X's is equal to 2, right?
Right, right. Now, I was very purposeful in making my 6 units be very messy, because
Yeah.
we'll have that all the time.
Mhm.
And when the numbers are larger or our students aren't very fluent with their facts, it's really, really tricky for them to think about that. So Chris, you definitely had the, I know I have 3 sets of 2, because you probably already knew in your head that 3 times 2 is 6. Some of our students don't have that. Can
Right.
you guys think of, if these are messy, like I had them a few minutes ago, can you think of another way that you could encourage a kid to know how to organize those chips?
I was making a connection to, I'm running a division intervention group right now where their first go-to strategy is always fair share. And this feels like a really easy application of how you can apply your starting division strategy to a complicated algebra equation.
Right,
Yeah.
right. Each X, each green stick gets 1 chip, or one yellow one, right? They each get 1. Okay, do we have any more to share with them? And then you go ahead and they each get 1 more. This is a neat, I'm looking at the time. Oh my gosh, how did that happen? I'm looking at the time, and this is one of those things for those of you who teach, well, this is mostly a 7th, this is a 6th grade standard, but we're still hitting it in 7th grade, and especially this year, we're probably still hitting it in 8th grade. With some of our more struggling learners who are still working on their multiplicative reasoning, that fair share is really important.
Yeah.
Because they're not going to know, if you have a bigger number like 4x equals 20, they probably don't know that 4 times 5 equals 20. So that sharing is great. And, you know, and a lot of times, you know, when we have a kid on the IEP and our classroom teacher may be saying, well, they don't even know their multiplication. How can they do solving equations? Well, we can use solving equations in the classroom to support their multiplicative reasoning. Because we can do this and say, okay, well, we have 3 x's. How many units goes to each of those x's? And then have them build an array. And then they're seeing that they have a 2 by 3 array makes 6. So we're really supporting their multiplicative reasoning. Goes back to the same one we just did right here. We can also support additive reasoning in algebra for our really struggling learners. If they're still working on adding and subtracting, just be really thoughtful about your numbers. Make sure when you're adding and subtracting that you always have, actually, to be honest, with a struggling learner, I'd keep everything positive. X plus 3 equals 4, right? And so they're trying to think, how many more do I need to get to 4? So they're practicing, they're practicing their additive reasoning, and they can do that within the realm of algebraic reasoning in their classroom. And so it looks a lot like all their peers, and they don't feel like, oh, I don't know this stuff. And, and then in 7th grade, when you go to multi-step equations, those struggling kids can still practice 1-step equations and work on their additive reasoning and their multiplicative reasoning. And to be honest, they could start working on integers in the same exact way with these really concrete models. I have 3 minutes, and I didn't leave any time because last time I looked at the clock, it was 5 o'clock, and I thought we had tons of time. But I do want to just talk super fast about, I just talked about how to differentiate a little bit. These routines, I think probably everybody knows stations or menus, or really work on dialogue. And I already mentioned when students are ready to stop using tiles, you'll see they're ready to stop, have them draw. And then when we're done with drawing, they can start using algebraic notation. One thing I didn't talk about was how to bridge the model to the algebraic reasoning and the algebraic notation. I use a strategy called brains, hands, and scribes. So the first thing I'll do is I'll set the kids up in partners, and one kid moves the tiles, but they're not allowed to move a tile without the other kid telling them what to do. So you have the hands and you have the brain. So the brain tells the hands what to do, and the hands aren't allowed to move without the brain telling them. Once the kids, and then you trade, do the next problem the other way. Once the kids have that routine down, you can then introduce the scribe, and the scribe goes ahead and writes what the brain says, tells the hands to do. So you have a brain telling them, you have a hand doing it, and then you have a scribe describing it in words. Then once the scribe can do it in words, then you go ahead and introduce the algebraic notation as the third piece of it. And so the scribe then goes ahead and starts scribing it in algebraic notation. And so you have all 3. The scribe can't write anything until the brain says something. The hands can't move anything until the brain can tell you. And it's really powerful to get the kids working in that type of a group to bridge from the concrete to the abstract notation. Oh goodness, and then that was not enough time. And then the last slide, I have this right here because it's a really neat one, and someone was struggling with surface area and volume when I gave this last time, and this is a really neat app by NCTM Illuminations. So if you want to play with it, it's there. And then this is a link to a Google slideshow that I created, and you can just click and it's animated. So you just click through, and it has like think bubbles and everything as so you could use it as a warm up or a model. You're welcome to it, you can have it. And like I said, I didn't really leave any time for questions, but I'd love to take any if anyone wants to stay. I know it's 5:30 on a Thursday too, though, so. Well, listen, thank you so much for sharing your time with us. I am excited that you're all here, and hopefully that you'll play with some algebra tiles if you don't already. If you want to stay on and chat and ask some questions, I'll stay on. So feel free to stay on.
Thank you all for coming.
Thank you.